Okay, this is a file which we had in the last week, and I think we done the meshing part. So let's open the meshing here first. And this mesh, I told you that we are not going to be right now be going through the details of the meshing software. So I just taught you the two commands. Number one is the generate option. Number two is the update option. So generate option will generate the mesh, and update option will actually export mesh to the Fluent solver in the Fluent format. Okay. So we just did this thing. And I told you that the mesh file format for the so uh, okay, so let me now tell you that we have the 3 to 4 files here. Number one is that when you save the workbench file, the workbench file will have the two files. One file is the with the extension of WBPJ, or maybe if this is like a zip file, then this will be the WBPZ. Okay. So the file name and then the dot and then WBPJ. This is a workbench file. And then inside the workbench, we have the one file will be for geometry. And the geometry was made in design molder, then the file extension would be .agdb. It's for the design modeler. And for a space claim, the file extension would be the scdoc. So let me mention this thing also here. This is the case when we have made the geometry in design modeler, and scdoc when the geometry was made in the space claim. And after that, we have the correspondingly, we have the mesh file. So mesh file will be saved in the .msh. And this is the typical Fluent mesh format. So this mesh will contain the only these like the coordinates like here. So we have the lines here, and these lines will be like having the XYZ coordinates. So on these coordinates, actually, we are going to solve our equations, and then we have to find out like maybe on this cell center. This cell center will be on the whole volumetric cell, this whole. Okay. So this 3D volume element, I'm talking about this 3D volume element, and also we have the one edge inside as well. Okay. So on this volume center, we have the one node. So we are going to solve, like, for example, in our case, we are going to solve maybe that we are trying to find out the variables like 3 velocities, velocity in x direction, velocity in the y direction, v, and velocity in z direction, and also the pressure. And but the viscosity and density, they are constant, so they will be like the same values as we input to the software or Fluent. So these values will be directly will be provided on all these nodes automatically because they are constant values. But if they are functions, if they are variables, and they are function of temperature, or in sometimes maybe it's function of pressure as well, so this mu can be the like a function of the temperature. And sometimes for the high pressures, mu can also be the function of both temperature and pressure. So in that case, the viscosity will also be one variable, and there will also be calculated on the different cells, and value will vary according from the one cell to second cell. Okay. So in that case, the when we solve case inside the Fluent has the two files. So one is the dot case file name and dot case. So this is like a case file. So case file is equal to the mesh file .msh plus the settings you make in the file, like boundary condition, turbulence model, like these things. And then we have the one extra file that is .date. So once you solve the case, so we have the date file that is like a data file, and the data file will contain the solution data. So full form is the data, and it contains the results. So like results, like I told you that this is the 3 velocities, pressure, viscosity, density. In some other cases, maybe different variables, like maybe it's the combustion chamber. Then we have the combustion properties there. So there can be many variables here on the single node. Okay, this is all about the how the files are there. So right now, where we are right now, we are here at this point. So we just made the file for the Fluent. So the next thing would be that now we have gone through these files, 1, 2, 3. So now the next step, there will be two more files will be formed, the case file and data file, okay? 4 and 5. And if you have any questions, you can ask me, and you can always put the question inside the chat option, okay? So now let's start with this part over here. Okay, so we just made the mesh without doing anything at all. We just click on the generate button, and then we just click on the update option. That's all. Okay. So right now you can see the quality right now is if you take a look here, and if you go to the orthogonal quality, this quality is right now is the minimum is a 0.67 and maximum is a 0.99. Okay, I think I have discussed the quality discussion or not. Did we discuss the quality?
No, we did not discuss.
Please, can anybody can confirm? Did we discuss the quality?
No, we did not.
Okay, okay, okay. Thank you. Okay, now let's take example with these elements. Okay, so if you take a look here on these element shapes. So the one shape is a collidator, second shape is a triangular. Okay, so collidator means that the any shape that has the four sides. So its perfect size is our ideal size. Ideal shape would be the rectangle. Okay, rectangle will be having the all angles are the 90 degrees. Okay, and if you see any distortion there, then this will no more rectangle. So this may have the general type of the collidator. This can have the shape like maybe like this. Okay. So at this point, when all the angles are, they have the 90 degrees. So we have the three quality matrices. One is the orthogonal quality. This orthogonal quality is basically is I would say it's a very comprehensive type of the quality metric. Okay, this contain the a lot of information inside there. So 1 minute. Okay, so this quality metric, orthogonal quality, just does contain the many information its angle and also the its connection with the neighboring cells. I will go through these all things. Okay, one thing is the orthogonal quality. So its zero value is the worst, and the one is the best. So you can see that one is best is the when the rectangle, the collidator is a rectangle. So at the moment this quality is the one. Okay. In this case, the quality may be let's say I put the name as a ortho. So short for the orthogonal quality. So ortho is 1, and here the ortho may be is equal to 0.3. Okay. And in case when the rectangle, this rectangle is now having the shape like this one, at this point, the orthogonal quality may be 0.1. Okay. So I think you are getting my point that how we are describing the quality. In a similar way, like we have second thing is we have the skewness. Okay. The only difference that the orthogonal quality having the 0 is the worst and the 1 is the best. Here the 0 is the best and 1 is the worst. So what does it mean? It means that right now this is not skewed. This is there's no skewness or there's no skewed the one line is not skewed to the as compared to second line. So they are not skewed here right now, all the sides. So right now, this is like a perfect shape. So there's the skewness right now is a 0. So at this point, the skewness is equal to 0. So in this case, now in this case, the skewness, I'm not saying this is they are directly connected, but somehow they will have the like a reciprocal definition. For example, if the orthogonal quality is a 0.1, then the skewness would be close to 0.9. Maybe it's a 0.95, maybe it's a 0.85. It will be close to that value. So we can say that the like the orthogonal quality and the skewness, they have the like a relationship like a. So I can say the quality in the quality form, the orthogonal quality I can say is equal to 1 minus skewness, roughly speaking, not 100%. This is like a very rough definition, not a mathematical definition, but roughly speaking, I can say this thing. Okay. So one is orthogonal quality, second is the skewness, and the third one is the aspect ratio. Okay, so aspect ratio is the like if the length of this collateral is the L and its width or height is W, then the skewness will the aspect ratio will be defined as the AR is equal to L upon W. Okay, now its value will be like I would suggest that it should be not more than 100. Okay, not more than 100. But in some cases, like in the boundary layer, like for example, we have the aerofoil. So on the surface of aerofoil, this can be like we can have the like large cells along the length of this aerofoil and very small cells along the normal to the aerofoil surface. And why this is so? Because the gradients are changing more normal to this aerofoil as compared to the if you take a look on the aerofoil surface. So the values are changing less along the along the length of the aerofoil, the chord length of the aerofoil compared to it is changing more in the normal to the aerofoil direction. So that's why we can have the like a large cells along the length of the aerofoil, but the small cells are normal to the aerofoil. So in that case, we may encounter aspect ratio up to the maybe 1000. Okay, it should be not more than that value. So it can be go up to the 1000. And but this is the limit for the single precision. So do you know about what is single precision? And aspect ratio can go up to the 10,000 if you use double precision solver. Okay, do you know what is the meaning of double precision and single precision? The single precision means that we have the memory that is using the 32 bits for storage. And double precision means that we have the 64 bits, means more, we have the double the precision as compared to single precision. So 32-bit means that now we can store number that is like as 32 bit. So for example, 0.001 minus the 0.001, 0.001. This is like a 1, 2, 3. Decimal also the 1 bit, 3, 4, 5, 6. And sign is also a 1 bit. So this is like a 6 bits right now. So in a similar way, this single precision can save our data, the numbers up to the 32 bits. So this is for single precision solver. But definitely when you convert this or change the solver to the double precision, this will be like storing up to 64 bits, but now this will be requiring double memory. So for the same mesh size, now because it is taking the double size in the memory. So for the same mesh, this will now require double mesh. So if like we were using the mesh size of the 1 GB for single precision, now like we have to use the double precision, then we have to be having the memory at least 2 GB. Okay. So now we can go up to the 10,000 when we use the double precision solver. So the question is that anybody, why we cannot use the like very high aspect ratios for the simulation? Anybody? Anyone, please? when you talk about the aspect ratio of 1000 and 10,000, so what will be effect on the simulation? See, when we have the mesh like this, any mesh like this, okay? So this mesh, now here we have the boundary condition that are, those are on the boundaries, okay? So these boundary values are fixed one. So we provide these conditions by ourselves. And then from these boundaries inward, we are going to actually solve the case, the results on these cells, okay? So right now, the cells where the solution is actually will be solving is on these 8 nodes, okay? So now what is going to happen is that the solution will propagate from this cell to this cell. And similarly, in the x direction, similarly, the solution will propagate from this cell to this cell. So from the like a boundary cells, solution will progress in this way. And then from this cell to this cell and from this cell to this cell. And there are two quantities. One is a scalar quantity and second is a vector quantity. Vector quantity is the quantity that has the value and the direction. And scalar quantity is a quantity that does not have the any direction but does have the some magnitude. So for example, the velocity. Velocity is a vector quantity. But the pressure is like a scalar quantity. Temperature is a scalar quantity. So these quantities are solved, for example, on the cell centers, and the fluxes are the velocity, like a velocity and other fluxes, they are solved on these faces. And also, when we are solving the for these vector quantities on these faces, what is going to happen? They are like actually when we have the two cells, so they are joined like in this way. Okay. So this line joining there, this is like going to decide on which point we are going to actually solve for these vector quantities. Now imagine that we have the like a large cells on the curve boundary. So what is going to happen now? Let's see, this is our curve boundary here. Okay. And we have the one cell that is like this much, very small height. And you know that if the one cell is like here, so, and second node is over here, this, then first thing is that the nodes are joined by straight lines. So this is also approximating the surface from curvature to the simple line. And the second cell, let's say, is over here. So we are going to join it in this way. Now imagine that we have to like interpolate data on this cell's face over here. So this is a one point here. So now that definitely the node will be placed over here. That is center of the cell, not the center of the geometry with respect to the boundary of the over here. So one node is over here, second node is over here. Okay. So now if you join these two nodes, what will happen? You will be getting line that is like this way. This line is going outside our mesh. So in this way, when the line is going outside, so if you integrate the quantities or you average the quantities on this point, which is basically not going through this phase, we are going to apply the values on the face. Those values will be wrong. Okay, if you interpolate the values on these faces of the cell, these values will be based on this line and they will be wrong over here. So now solution is that either we have to increase the cell size, like height this way, or we have to increase the lengthwise or the streamwise cells more there. So then if you like add the height more height here, then the definitely aspect ratio will increase. Or if you add the more cells here, aspect ratio will also increase. Okay. So these all things will lead to the better quality solution and the better quality mesh. So aspect ratio it should be kept in some limit, like in the free flow means not modular, then it should be like not more than 100. And in the modular, we can go up to the 1000. Okay. So this aspect ratio and skewness, they define, and one more thing I will discuss here, they actually define the orthogonal quality. So orthogonal quality contains the skewness, aspect ratio, and the fourth thing is the uh, volume ratio change. So this is like a volume ratio change should not be more than 1.2. So you have seen this thing in CFD. They say that the first cell is, let's say the first cell is this one, The second cell should be multiplied with this first cell height. This is the length of the cell, multiplied with the 1.2. So this is like if the first cell size is 1, then second cell should not be more than the 1.2. Third cell will be the 1.2 times of this cell, which is 1.44. So this is like if we talk about this a two-dimensional, if we talk about three-dimensional, this is going to be volume. So it means that the volume should not change more than 20%. If we talk about the 1.2 times the next volume should be, it means that we are limiting the volume change not more than 20%. So again, if you change the volume, same thing happens as a aspect ratio. So but that is on the volume base. So if you change it more than 20%, then again you are going to be having the wrong results on the interpolation on the different phases. So these three things, skewness, aspect ratio, and the volume ratio change. So they combinedly will define the orthogonal quality. So now question is that what should be the best value for the orthogonal quality? So I will discuss this thing. Okay, so let me make another slide. So okay, so we are trying to actually I'm trying to explain the different quality matrices. So now question is that because I said that the skewness, which is like about the angle of the element, then we have the aspect ratio that is like the ratio of the two sides of our cell. And third thing is the volume ratio change. That should be not more than 20%. So these all things combinedly will define the orthogonal quality. So what should be range here? So orthogonal quality at least should be not less than the 0.01. So this is the minimum quality we should be having. This is defined by the Fluent manual. So this is the minimum quality that we should have in the mesh. Below this value, we cannot accept the value, and this will also give you warning in the Fluent. So this is the minimum quality that we are requiring to have in the mesh. Then we have the like quality from the like a 0.01 to the 0.05. So this is like I would say very poor quality, but it's okay. This is very poor quality. So, and then from 0.05 to the 0.1. 0.15 is a like I would say is a fair quality. So if you can achieve the 0.15 or more than 0.15, then we are going to have the very good quality solution or simulation. This is a fair. And then from 0.1 to the 0.3 is going to be the good. And anything above the 0.3 to 0.7 is like a very good. And 0.7 to the 1 is like a excellent quality. Okay, so these things you should be like looking for. And in a similar way, like we did the define the quality for the rectangle, same thing happens with the triangular element. So again, the triangular element, the perfect triangle will be the equilateral triangle where all angles and all sides are equal. That is the when angle 60 degrees. So anything different than 60 degrees will be actually having the low quality. For example, if my triangle shape is like this one. So maybe in the first case, the orthogonal quality here, it is like 1. Okay, that is the best. And here orthogonal quality may be approximately equal to the 0.2. Okay. And in a similar way, I would suggest that if you have the like a rectangle or rectangular, whatever it is, so definition will apply into the both element type equally. So sometimes this happens that this is the one side of the triangle. This is the second side of the triangle. And the fourth side somehow is actually like may go in this way. And then it joins this element this way. So there is some like extra geometry that is like the original definition would be that it should be this line and this line should have be joined by together by the one line like over here. But now it is like a distortion and it is like going up and then joining here. So this is like in terms of the volume, I would say this is the natural volume would be here. That is the positive volume or the positive area. Okay. And this is like a negative side. This is like a penetrating and it is going inside itself. This is a negative side. So sometimes you will see this warning that we have the negative volume or negative quality. Okay. This is the definition of negative quality or negative volume. So negative volume or negative area two-dimensional will always lead to the negative quality. This should be avoided at all the costs because now we are actually not solving the our triangle but we are solving something else. And the neighboring cells, because neighboring cells will be here. They will be here. Okay. The neighboring cell may be of the good quality, maybe it's over here like this. So it has the proper edging, three edges. So now it will get confused that it should be like this edge should be common, or this is going to be with this edge. So it will get confused, and you will be like hard time to get data from one cell to second. So this will like always go to divergence at the immediately. Okay. So negative volume is always is not required. It's like not possible for CFD. Secondly, we have the zero volume. Zero volume is that when this triangle like collapse to the like a one line. So these three edges may join together and this make a form a one line. This is zero volume. So zero volume and the negative volume are the like they are not acceptable in the CFD simulations or CFD measures. So you should always be looking for zero volume and the negative volume. Volume can be very low. For example, the size of the element can be very small, and the volume minimum volume can be of the very low volume. Maybe this 10 power minus 10. That's okay, but it cannot go to the zero volume or negative volume. And these are the values ranges for the orthogonal quality. So what I'm trying to do, I'm trying to at least have the 0.01. My target is that I should be at least having the 0.05, and my like prayers will be like I should be able to achieve 0.15. So in between, this is like this is my minimum target. Okay, this is my minimum target. So on that minimum target range, this is my minimum range. This is my upper range of my minimum quality requirements. Okay, so I think you understand this thing. Any questions, please?
Yes, and
So now you can see that. Yes, please.
well, I don't know if we're going to explain this, but how can we fix that problem if we don't have the if we have the negative
Actually,
value,
fixing
the negative quality?
fixing the problem is that always we have to be go for the better like a cell size definition. Like if the cell size is defined is a very large cell or very small cell, or maybe there is a like if you define like for example if you put the less cells here, this will always lead to the low quality. So the volume change, you can see the one on this side, this is like a very large cell, and then cell here is very small. Then you should be trying to have the put the more cells here. Okay. So that you can do by yourself. So this will lead to the better quality. And if the elements are skewness, so its skewness will always be because of the geometry curvature. So divide the geometry into the parts so that we can have the like more control on the element shape. Okay. So that is doable.
Thanks.
For triangular mesh, this is mostly automatic. But then I would be suggesting solution would be like you have to put the more cells in some location or maybe less cell another direction. This will solve the problem. Okay, we'll see this thing. Okay. But first we must know that what is the required and what is not, and what is not acceptable, what we are trying to achieve. So this is what first thing is that we should be knowing that thing. Okay. So this is what we have. Okay. Now, if you go to the element shapes, so in the three-dimensional, two-dimensional elements are the quadrilateral, and in short, we call them the chord. Okay, that's why you see the chord elements. Okay, And then the triangular element, the short form is a tri. So that's why we have the chord element, tri elements. They are coming from these few letters from its full name. And in a similar way, like we say hexahedron, so hexahedron is a geometry shape that is like a cubical shape. Cube is like a perfectly square shape, all sides are square. But hexahedron is like similar to the cube, but the sides can be of the rectangular shape, means that not necessary to be square. So that is called hexahedron. So the hexahedron is like a short form is the only hexa. Similarly, tetrahedrons, this is a combination, this is a three-dimensional feature, three-dimensional geometry figure, and this has the like a four triangles, and they are joining together. So one triangle, second here, third on the back side, and one on the bottom. So four triangles combining, they call tetrahedron, and short is a tetra. Pyramids, like you know about the pyramids of the Egypt, like so that is like a base is rectangle, and the four triangles will meet at the one point here on the top. Okay, so that is the pyramid, and the prism has the like in the CFD, the prism is see, always we in two dimension we always go for the like a chord element. It's the best. And 3D we always go with the hexa. Why? Because it has the more sides, more sides. Okay. So chord element can get info from here, from here, from here, from here. So it can have info from the four neighboring cells. So it will be like we will be able to solve this mesh in the less time, less iterations. Okay, this will be like have the less diffusion. Less diffusion means that the solution will be like diffusing, like viscosity. So if you put the ink in the water, this will diffuse to the sides. So this will be like more diffusive in a triangular mesh. In collinear mesh, the solution will not diffuse, and it will be contained to its particular value on that cell. Okay. So triangle has a three surfaces, faces here. So it will get information from the only three sides. And one more thing is that if the flow is going in this direction, so all the normals will be correctly like predicted by the collinear cell. But in the case of triangular cell, the flow is going in this way. So its normal is going to be here, but the actual phase shape is inclined. So then we have to like apply the different interpolation schemes to get data on this surface here. So this will definitely introduce some errors here, and then we will be having the now imagine that we have the multiple like 1,000 of or maybe 1 million or the 1 lakh these type of the faces which are not normal to the flow direction. So definitely we will be having some errors on those phases. So those errors when they combine together, they will like sometimes may lead to the divergence or some errors, large errors in the solution. So always we try to avoid the like triangular mesh. But problem is that chord elements cannot fit very well to the geometry. See, if this is my geometry, okay. So now having the chord elements, then on this corner, it has to be like having the very controlled here, okay. Otherwise, quality can be low. And here, maybe one element is like this. So here, how we divide the element, how we put the element here. But if you take a look on triangle, triangle can adapt to the any geometry very well. Okay, they can adapt to the any geometry very well. So triangles are easy to create. Triangles are very easy to create, and it can capture the geometry very well and without any spatial control. So triangular mesh is preferred because for complicated geometries, collinear mesh may take time. For example, if I talk about the wind turbine meshing with the collinear elements, this may take maybe a few weeks very easily. But triangular mesh can be like computed within maybe 3 to 4 or 5 hours if you know the software. Okay. So any commutator mesh can be computed within 5 to 6 hours very easily, or maybe less time. But with the hexa meshing or chord elements, this may require a few weeks. Okay. So definitely, if you are able to make the high quality hexa mesh, a chord mesh. Second thing is the quality, because with different geometrical features like sharp edges, so collators may not be able to, we may not be able to produce them. So first thing is that we are having difficulty into the mapping the chord to the geometry. Second thing is that to have the decent quality. So those things are difficult to achieve with the collateral or hexa elements, but these things are easy to achieve with the triangular mesh. So now problem is that when you are talking about the like a monolayer mesh, like for example here this is a flat plate. So this flat plate will be having a like a boundary layer here. Okay. So to resolve boundary layer, we need the more nodes towards the like high gradient regions. So triangular elements, and also they should be aligned to the our geometry, our flow. So uh, triangular elements we cannot actually, if this element like right now this one is here. Okay. Now if you try to get the small element size here to capture the like having the velocities now different location, maybe at least we should be resolving at the 20 locations. Now initial element size is this one triangular. So if you try to like compress it, so this element may go in this way. So this can have the like, if you take it like a down here, this may have the like low quality, high angle here and the low angles here. Okay. But if you try to compress the rectangular shape, a chord shape, if you compress them, like if after compressing them or reducing their height, they still will maintain their shape. But triangles, when you compress them or when you have reduced their height, they will be distorting their shape. So their quality will automatically go down from maybe it's a perfect one quality. So they can go to the quality of the 0.05 without doing anything else. We just compress them to it should be able to like solve the boundary layer flow. So it means triangular elements that they are not suitable for the boundary layers. Okay, triangular elements. A tetrahedron is three-dimensional. So then we should be going for the like hexa meshing, but hexa meshing has the difficulties in creating the mesh, good quality meshes, and the for complicated geometries. The solution is that what people right now is doing is that they put the triangles in the like rest of the domain, but in the boundary layer, they put the prisms. Why? Because see, on the surface and top, they have the triangular shape, but on the normal to the surface, if you take a look from the side view, this is rectangle. So if you place element in this way, so from side view, they are the rectangles. So if you reduce the size, like they will be still rectangles. So triangle will be triangle. They will not be distorted because they are only on the bottom and the top. And if you compress them, if you reduce the size, their height, they will be still having maintain their quality. So that's why in nowadays what they do is that they go with the prisms in the boundary layer and and the tetrahedrons in the rest of domain. Okay, I think this answered your question. It's okay. Okay, then question is that we have the like a tetrahedrons and the prisms. Hexahedron is difficult to create. It's difficult to create. So now question is that what is the function of pyramid? The function of pyramid is that when we have the prisms in the boundary layer and rest of domain is tetrahedrons, sometimes there may be some gap is there that cannot be like filled by the joining the tetrahedrons. Definitely the sides are the triangles. So they are will be like from here to the, then the one side will be here, three side will be outside into the domain. Sometimes there may be some small gaps are left and that cannot be filled with the help of the prisms and tetrahedrons alone. So in those gaps, pyramids will be generated. Okay, and for fluent, we are going to avoid the pyramids at any cost. Okay, so for the fluent, we should be avoiding the pyramids. So try to have the better quality prisms so that the because if you want to have the better quality prisms, so they have to have the some parameters defined properly. If parameters are defined properly, the software will try to have the better quality prisms, but then it will add the parameters into the mesh. So try to avoid parameters at all costs because the Fluent doesn't like it. Okay, so now we can see that we have the like these all definitions and the requirements here. And same is true for the triangles also. Okay. So now if you take a look here, the quality, orthogonal quality minimum is a 0.67. So I told you this is like up to the very good quality, okay? But also you should be take a look on the average. Average is a 0.95. So what does it mean? It means an standard deviation is like a 0.05. So now if you know about the normal curve, you know this thing exactly. Then what is the meaning of this thing? This means that if you take a look on your normal curve, so it means that your majority of the cells, they are around the 0.95. And your minimum element is like 0 is over here, 1 is over here. So minimum is like maybe is a 0.67. And it also says that the standard deviation is a 0.05. So standard deviation is the 0.05. So very less element, you can see less elements are on this side. Major elements are there on this side. So 0.95, and then if you go on this side, so majority is over here on this side. So very few elements, they have the quality that is like of 0.67 or between 0.67 and 0.95. Even if this is 0.67, very few elements are there, but majority of them are maybe like a 0.7, 0.8, 0.85, and 0.9. So from my point of view, this quality is very, very high. Okay. So from my point, this quality is very, very high. And definitely, why it is high, if you have the, like, if you can take a look here, element shape is like they have the like large size here, and they are moving freely. So that gives them the high quality. But once you try to have the more cells in the boundary, like over here, normal to the surface, then the quality problems will arise. Okay. Not for this problem, but for the majority of the problems, the quality will arise. Because we have the requirements to resolve the flow features, and to resolve flow features, we have to like a very small cells. Small cells will lead to the maybe sometimes distorted element shape, and this will lead to the low quality. Okay, one thing is that the quality. So, and also right now the minimum quality is a 0.67. And I told you that skewness is not exactly the 1 minus the orthogonal quality, but roughly speaking, it will be like, it should give you the values around that value, okay? So if you take a look on the skewness, so 0.67, if you now take a look here, 0.67 minus 1, it's around 0.33. So here it is showing that the maximum quality is the 0.43. So, like I told you, skewness, 1 will be worst and 0 will be best. And for orthogonal quality, the 0 is worst and 1 is the best. Okay. So, there it was a 0.67. If you separate from 1, the 0.3, but right now it's a maximum quality is a 0.43. So not 100% they are equal, they are same, but you can get roughly idea that it is close to this value, 0.33, this can be 0.4, maybe it's a 0.25, okay, like that. Okay, second thing is the number of cells. So there are two things here. Number of nodes and number of elements. Number of elements are the same as the number of cells. So that is like when you talk about this thing, the elements, so cells are the cells which have the volume, okay? And at the center of the cell, we have the one node. Similarly, at the center of this tetrahedron, we have the node. So for every element, we have the like one element corresponding, we have the one node there. And also there are nodes on the on the boundaries. So where these cells are intersecting the boundaries, they will be having nodes also there. So that's why nodes may be slightly different than the number of the cells. So if you take a look here, you can see this thing. The number of nodes are 20,000, number of elements are 18,000, because we have the extra nodes on the faces, like on these boundaries. Okay. So there are the like 18,360 elements, and all elements are it is showing the wedge 6. The wedge 6 is a prism. The wedge 6 is the prism. And not all very small, they are the prisms, and majority is the hex 6. head. So hexa 8 is like defining the number of the sides. So if you take a look here, the number of sides in every element is like in the case of hexahedron, this is like 8 sides. So that's why they put the name as a number as a 8. So it is to clarify that this is a properly hexahedron, means we're having the, it will have the 6 sides, but it will be having the 8 nodes or the 8 vertices. So you can see here. 1, 2, 3, 4, 5, 6, 7, and 8. So 8 means that we have the 8 vertices. This is only for the hexahedron. For tetrahedron, there will be the 4 nodes, okay, on the corners. So element, then there will be written as a 4. For triangle, this will be written as a 3. Okay, tri and then 3. It means this is a 2-dimensional element, and tetra and 4 is a 4-dimensional element. And pyramid will be having the 5 points or vertices. And prism will be having the 6 vertices. So you can see we have the hexahedron. That's why it is written as a 8 in front of the name of the element shape, and prism. And then we have the, so prism is called wedge also. It's a wedge shape. So wedge, and we have the 6. So you can see we have the wedge 6, that is the prism element, and hex 8, this is actually hexahedron element. So the number of elements right now are 18,360. Okay, now the last thing that I want to show you is that if you go to home menu.
There's one question, that what is weight 6? It's a prism element.
6 is the number of the vertices on the your shape.
Okay.
This is how they identify the different geometrical shapes, but this is what it's the meaning of those names here.
And sir,
Okay, now just click.
from where they got the word weight?
Wedge. This is not a wedge. It's a wedge. WEDGE.
Okay, GE.
So
okay,
wedge. You know
okay,
about
wedge.
that how? Okay, wedge. So wedge shape is you know about the wedge shape, that is like
Yeah, I know.
there's a one line here on the sharp corner, and then we have the like on the back side we have the one face.
Okay.
Okay. Okay, this is actually hexahedron. So short form is a hex, simple HEX.
Sir, will we use wall function, or we will create a boundary layer?
We will
Will we create a boundary layer for the pipe, or we will use a wall function?
No, we are not going to add boundary layer right now. We are just going with whatever we get by clicking on the generate button only. So we are going with without doing anything else. We just click on the generate. Whatever we get, we are going with that one. But definitely we need the fine mesh in the boundary layer.
Okay, thank you.
Okay.
Okay.
So right now I'm just going with the flow. I'm just not going. I'm not introducing any complexities here. I'm just going with the bare minimum. Okay. So definitely these things, the information you are seeing here, will be same for all the meshes. Okay. So you have to look for the mesh quality. You have to look for the number of cells. That's important parameter to be reported. And then definitely you have to see that the physics preference should be CFD. So based on the CFD, there are the 5, I think, fields, 6 fields: mechanical, nonlinear mechanical, electromagnetics, CFD, explicit dynamics, and the hydrodynamics. So for different algorithms, they have optimized the different meshing program inside the workbench meshing. So based on the preference you choose here, those options will be activated or deactivated. So be careful. Sometimes maybe by default you have the selected, because majority of the cases I've seen, the mechanical is set. Okay, so whenever you have the mechanical as a physics preference, many options for the meshing will not be available. Okay, because for mechanical we don't need those options, or that type of mesh we don't need for the mechanical application like FE analysis. So you have to change it also to the CFD. And then we have the 3 solvers here. So right now we are going to work with the Fluent. That's why we chose the Fluent here. Otherwise, you can have the CFX or the Polyflow. So polyflow, you know about this, like a non-nutrient fluid and for extrusion purpose. So either we have the CFX or fluent. Majority is using the fluent. Okay. And then we have the like inflation layers that we're talking about, boundary layer mesh.
Sir, how
This is a global inflation layer.
so there is a question that how do we select the solver preference?
Mm-hmm.
What's the selection criteria of solver
How we?
preference? What's the selection criteria of solver preference?
Solver preference is like now if you select the fluent, the mesh format will be the .msh. Okay. So if you choose the like a CFX, the meshing format will be the CFX.
Okay.
Okay. So for example, if you choose the fluent as a physics preference, the mesh output will be like .msh. It's a mesh format for the fluent. But if you choose a CFX, then the mesh format will be the CFX5.
And so for this problem, why we are not selecting CFX as a solver preference?
CFX, we are not choosing. One thing is that because in our course, I said I will be using the fluent. Secondly, why I chose the fluent, because majority of the people they are working in the fluent. But if you even go with the CFX and the fluent have the almost similar features. Okay.
So they both will give the same result.
What will?
They both, the fluent and CFX, they both will give the same results.
Yes, definitely. They will give us same results. But now, for example, I tell you that if, for example, if you want to specify the angle of attack, like in the fluent, we just give the cos and the sine theta components. But in the CFX, actually, we have to define those functions first. Either by defining the functions, then we have to put the values for the angle of attack, or we have to define the a new coordinate system in the CFX. For example, this is my x and y. Okay. So if I want to apply the angle of attack of 10 degrees, I'm just exaggerating the angle of attack. This is 45 degrees, but I'm just to explain, and the graph should be very much clear. So I'm just saying this is like a 10 degrees angle. Okay. So now if I want to specify angle of attack in the fluent, I have to give the x component as a cos of 10 degrees and the y component as a sine of the 10 degrees. Very simple thing. Okay. But if I go to the CFX, for CFX, I will be either defining these x and y components, then I will be defining the angle. Like I have to define angle of attack. Then I will define the x component, that is cos of that angle, then sine of that angle. And then I can specify those parameters into my inlet conditions. Okay. So mostly people don't like it. Second thing is that whenever you export the mesh for fluent and import mesh into the fluent, you will always see the boundary conditions like inlet, outlet, wall. But in CFX, you will not see those boundary conditions directly. You have the one volume domain, and also inside they have those names for the boundary condition. But you have to produce or create those parts again by yourself. It's a little bit more work there. And second way to specify the angle of attack in the CFX, that you have to like rotate your coordinate system. So for example, now new coordinate system will be like this. This will be my new x. This will be my new y. Okay. So now if I give the like a 0 degrees in the new coordinate system, this will be equal to 10 degrees in the like original system. Okay. So like I have to create a new coordinate system that will be rotated by 10 degrees. So this is the second way to give the angle of attack in CFX. So, but then we have the like in CFX, we don't have the boundary condition type, that is a pressure far field, which is commonly used for the aerodynamics. We don't have the pressure far field.
Okay.
And then also we have the like in CFX, we have only one solver, that is coupled solver. Coupled means that it is coupling the momentum and the continuity equation. But in the Fluent, we have the simplex and the piezo. That is like they are not coupling, but they will solve the continuity and momentum equation in a loop. Okay, sometimes this is maybe better for some applications. And pressure far field condition is like you can specify directly Mach number. So that condition is not available in the CFX. But then for the some problems, the CFX has a more powerful interface, simple definition for the problem physics, and sometimes it is more complicated than to CFX than the Fluent. So I would say that for all softwares who are working on the CFD field, they all are solving the Navier-Stokes equations. Okay. Now, how they are implementing the Navier-Stokes equation, that will be like contributing to the accuracy and the speed of the solution. But nowadays, I have seen that all softwares they are pretty fine. They are giving the very nice results. So now it's your preference that which software you are preferring for your work. Okay, but definitely now if you want to go for OpenFOAM. Okay, this is a free share where you can download and you can use it for free. Now, problem is that, and the benefit is that for the OpenFOAM, they can have some solver features which are not available in CFX or Fluent. Why? Because somebody implemented into the OpenFOAM some solver features, new turbulence model that is not tested very well. But you can risk it, and you are risking for that one, and maybe you are lucky you can get the good results. But when it comes to the commercial software like the Fluent or CFX, they will thoroughly test that feature, and maybe they will add that feature after 5 years once it was first published in the literature. So this is a problem with the commercial codes and these open or free share codes. But problem is that the OpenFOAM type of code, they don't have the proper interface. So either you go for some company that is making the interfaces, and they will charge a lot of amount to you. Like there are some companies that are working. One is in the Germany. I don't remember. They are based on the cloud based. So they charge a lot of money. They are using the OpenFOAM, which is free software, but for their interface, and interface for the input like pre-processing, and output for the output post-processing, and the meshing, which is they made it very simpler to create. So they are charging a lot of amount there, but those things are already there in the commercial softwares. Like meshing software we are learning here has a more features than the OpenFOAM. Okay, but definitely once you make the mesh, all meshes will have the same features. They have the cells and they have the coordinates, XYZ coordinates. So they will always lead to the same thing. But how you proceed to the destination is the point of the concern. So sometimes the things are difficult, and sometimes things may be very simple. So preference is your personal choice. Now imagine that right now at the moment, you have a lot of help available on the Fluent. You go to any forum and you put the question for the Fluent, you get the answer. But if you go for the CFX and you put the answer, maybe you will not get answer. Answer might be for 2 years. But for Fluent question, you get maybe 10 answers within 1 hour. So that's the point. Okay. Okay, so now we have this quality, and now last thing is that for every mesh in the ANSYS meshing, you have to click an update. So update will do the two things. Number one is that it will be checking everything in the mesh. There's no warning, error, or any problem. And once all things are cleared, everything is checked properly, then it will export mesh in the proper format. For example, for the Fluent, it will export mesh for the Fluent format. This will give you a message that mesh translation to Fluent was successful. Simple. Okay, then you can close the mesh. And please don't forget to save your project file time to time. Okay, and sometimes in case of the power failure, sometimes maybe there is errors in your computer. Sometimes your software license was based on your network card, and network card is based on your Wi-Fi address, and Wi-Fi was switched off. In that case, Wi-Fi is not working, and your software can close down because it will not be getting the license server. So always be saving the file from time to time. Okay, next thing is that we are going to open setup and run the case. Okay. So that we will do after like 10 minutes. So I will come back at the 8:15. That's all. That's okay. 8:15. Hello? Can you start again? Okay, okay. Thank you. Okay, sorry for the late. Okay, so okay, now next thing is that we have to like double click on the setup and open inside the Fluent. And for this simple problem, I don't require double precision. 32-bit system is okay for this problem. This is very simple problem. And number of processors, I will be like, okay, then let's discuss about this thing, okay? So, you know that everybody knows this thing, but at the moment, I think I have the very less cores in my computer. So in my computer, it's only 4 cores, okay? But there are the computers, laptops, they have the like 20 economic cores and maybe there are the 4 performance cores, okay? So ENP cores, you know about this thing. If not, then you can search on the economic course and the performance course. In the Google, you will find that what does it mean by these things, economic and performance course. So economic cores are like used for the simple processes like Windows applications, like a Word, PowerPoint, or any background application of the Windows. And performance cores are basically used for the like mathematical calculations where it requires more power. So you can have the like at the moment, many people have the like at least maybe 20 cores. 8 cores are very common for a long time. So 20 cores are there, maybe 40 cores are there, maybe there are 16 cores. So a lot of numbers are there for the cores. So what should be the selection of the number of cores? Number one is that the memory should be also in your computer installed in the 2 power n. This 2 power n is for the computers. And same goes with the number of processors. So if the n is equal to like 0, then 2 power 0 is equal to 1. If n is equal to 1, then 2 power 1 is equal to 2. So 1 core, 2 cores, and 2 power 2 is equal to 4. 2 power 3 is equal to like 8. 2 power 4, 16. 2 power 5 is equal to 32. 2 power 6 is 64, and so on. Okay. So, but the number of cores we are getting in nowadays, they are not in this sequence. They are like 20, sometimes 16, maybe they are 96 in your whole computer. So choose them in wisely, okay? So rule of thumb says that if our mesh size, if the mesh size is like, is the number of cells are the 1 million. 1 million, you know that it's a 10 power 6. Okay, so 10 power 6 means that 6 zeros. 30 and 30. So this is the size of the mesh. So 1 million. Okay. So if the 1 million cells are there, then for this 1 million cells, we need the RAM as the at least like from 2 GB to 4 GB, depending that how many variables we are solving, how many physics are involved there in the solution. So 2 GB to 4 GB for 1 million cells. Okay. And then also we have the rule of thumb for the number of cores. So number of processors like, so for 512 cells, that is like a 500,000. We at least need a 1 core. Okay. But if you have the more cores, then you can like go to the 256 cells, 256 million cells, 512K, 256K. Okay. This is the quarter or 1/4 of a million. So you can have the 1 core, but at maximum, I would not suggest that the for the 1 million, at least there should be the 1 core. Okay. So now let's say in some problem, maybe you may not be having that problem. Let's say our mesh size is 20 million. Okay, so I would be requiring the, at least for the, when the flow is compressible, then I may require the like a 80 GB RAM. And when the flow is incompressible, maybe I require the 40 GB RAM. Okay. So for these problems, when you are solving like a flow over an aircraft that is a compressible flow, you would need the 80 GB RAM. So you should be going for the system which has a 128 GB RAM. In this case, go for a system which has a 64 GB RAM. Okay. And for 20 million, if you go for the middle value, then that's a 500,000 is a one core. So means that you need the, so 20 into 4 into like 2 is equal to 40 cores. Then I would suggest you should go system with a 64 cores. So nowadays 64 cores and 64 GB RAM or 128 GB RAM is a very common. So 64 core system and 64 GB RAM or 128 GB RAM is the good to go for the when you are working in the CFD domain. But definitely it's a very costly and sometimes we cannot afford. So you can go for the low system, but then the solution time may be very large. Okay. So right now for this problem that is containing the only 20,000 cells. Okay. It's not it's a 20K cells. Okay. Like we were talking about the 512, 256 cells, 1,000 cells. It's only 20,000 cells. Not 20,000 cells, but it's 18,000 cells actually. So for this, one core will be enough. So you can choose a one core only. Okay. So then the question is that what will happen if you choose the more cores? Actually, more cores means that like we have the cores here. Okay. So they have the they have the cache memory, and then they have the proper RAM here, and they have the hard disks. Okay, they can be the SSD or maybe hard disks. So for the quick task, the CPU will transfer the information to the cache, and when it needed, it will take it back to the its processing unit. And also when we have the large problem that will divide into the small parts, and small parts will be solved in the different cores, and definitely they will be combining their information after some interval. So they will be like writing and reading the data all the time. And then they will also put the data into RAM whenever data is not required, and they will take the data from RAM when the data is required. Okay. So now imagine that we have the small problem, so that requires storing data into the RAM again and once, and then and more it is transferring data from one core to second core, but actual processing time is very low. Like it's a very simple problem, it can be solved in a very in a single go. So now it will spend more time, it will waste more time in the reading data, writing data from the its different cores and the memory and the cache as compared to solving directly inside the one core. So in that case, the one core will be efficient because it will lose the time in data storage and the data retrieving. So you should be careful. So sometimes people complain that they are using the 64 cores on a very simple problem, and solution is slower than the his friend's computer having the only 4 cores. So the problem is that because it is wasting time in data reading and writing. So you should be understanding this thing, that you don't require always the more cores. More cores maybe means that the data will be distributed and it will waste more time between the different cores. Okay. So be careful about this thing. So single core will be okay for this case. Single precision will be okay for this problem. And click on start. Okay, first thing that you will see that either you can go to these menus here, and for every menu we have the options. And the same thing is also available over here on the left side. So for some cases, I prefer the working on these vertical menus, vertical options, and sometimes I will go to the options over here. For example, if we want to provide the operating conditions, then I can put the operating conditions directly from here, or I can go to the conditions over here. It's a boundary condition. And we don't have the operating conditions over here. So reference values you can always give from the here. Okay. Or you can go to results and then you can also put the reference values. Or you can put the reference values from here. One minute. I cannot find it. Okay, let's leave it. Okay, so there are many options that are more easy to use. For example, I have the domain. I want to adopt the my domain. Okay. So adaptation is like a very easily available over here. If you want to solve the turbo machinery workflow, is available here. So you can enable the turbo machinery workflow, and it is a more option now in the new versions. And similarly, we can work with the dynamic meshing that like requires the meshing is like a distorting, or maybe it's recreating new elements. So like some element is moving, like a boat is moving in your domain. So that may require dynamic meshing application. We have the mesh interfaces, and those can also be defined over here. Mesh interfaces, same thing over here. Okay. So the first thing that I have started is a journal. And from here, I told you the scale option is here. Scale option is like, it's not required here when you work directly in the workbench, because we are having the proper synchronization of data. So data is synchronized. So geometry was made in the millimeters or the meters. It was recorded in the workbench, and same information will be transferred to the meshing. And from meshing, this information will be transferred to setup. So our scale will be same throughout all the apps we are using here. But in the old times, because the Fluent was purchased by the ANSYS some time ago, so Fluent can accept the meshes from the different meshing apps. So meshing apps don't know about the geometry units. They are like they are unitless. Okay. So if the geometry was made like for example, the cylinder length is 10 meters. So they will not take it 10 meters, but they will rather take it 10 units. Okay, 10 units. So whatever units are. So now imagine the geometry was made as like not the 10 meters, but as 10,000 millimeters. So the meshing software will take it as the 10,000 units. Okay. So mesh will be created and will be exported in the 10,000 units. But the problem is that the Fluent is based on because it has to be maintain the some dimensional quantities intact. So it is based on the SI system. And so, for example, it will always work in the meters, in seconds, in kilograms, in Kelvin, like that. Okay. So whenever any data which comes to the Fluent, it cannot its internal working will be always based on the SI system. You can input data in the other system. You can get the data output display in the other systems. Internal working is based on the dimensional values of the SI system. So whenever we take the mesh from some meshing software, like outside the ANSYS in the old times, so it was like now 10,000 units. But because Fluent has a tendency to always work with the meters, it will assume this is like equal to 10,000 meters. So now imagine that the geometry was like made in the millimeters, and it was 10,000 millimeters. And in meters, it should be like 10 meters. So Fluent will like take it as a 10,000 meters. So this will be wrong thing. So that's why they have given the option to actually convert this mesh back to their original units. Okay, whatever the Fluents are, Fluent is assuming that they will take it back to their original dimensions. So length, diameter, and height, width, they should be equal to the whatever is originally done on in the geometry model. That's why we have these things over here. So for example, now imagine that this length is not 40 meters, but it is maybe it's a 1 meter. So by some units, we have the 40 meters. So what we have to do is that we can specify our own factors. So I have to divide everything by the 10. And then I can get a Z is equal to 4 meters. So if I scale, So sorry, I have to multiply with the 0.1. And see, this is now 4. So if this is wrong, then you can unscale anytime against the 40. So let's say the units were made in the geometry was made in the millimeter. So if you scale, this will multiply everything by the 0.001, means that it will change them into the millimeters, the overall dimension of the geometry. Okay, so scale. So this is like a 0.04. If this is wrong, then you can always unscale. Okay. And here you can see the view units. So view units, length units are there, like you are just viewing them in some other units. For example, you are more comfortable with the inches or the feet when you are working in the USA. So you can see them, the X and Y and Z coordinates in the meter, in the feet. So, okay, so this is just for viewing purposes. It will not affect anything in your mesh. So then close. And then the check option here. Check option actually is useful when you are looking for the mesh quality, generally speaking. So click on the check. And the most important thing, you can see here, you can also get the errors. If there's some errors in the mesh, so errors will be like on the bottom. So errors should be taken very, very seriously, okay? And they should be solved before you will be able to solve the case. But here, the most important thing is the minimum volume. So I told you this minimum volume should not be the negative or the 0. So always look for the minimum volume by clicking on the check option, and the minimum volume should not be negative or 0. Otherwise, we will not be able to run the case. So once we get the negative volume or the 0 volume, then go back to meshing software and solve the problem there and then come back into Fluent. Okay. So we discussed about the negative volume and the 0 volume very thoroughly. Any questions? Okay, then with the report quality. So report quality will give you the two matrices. One is the orthogonal quality, which we have seen, that is 0.67. And the maximum aspect ratio is the 4.4. That is the length divided by the height of the cell. Okay. So when you go for the boundary mesh like impression layers, you will see that aspect ratio will increase to the very high values. Okay, then we have the mesh verbosity that you can display here. So for example, if you type the mesh here, there are the many options here. So if you click on the mesh, okay, and then we have the option that is like a check. So one is check, second is the quality. So you can also do the same thing from the text menu. Okay, so we have the mesh quality, and I'm looking for the we have the some command that can give us the more information. Let me check it. Just 1 minute. You can always search on the Google about the different text commands. Just 1 minute. Just 1 minute. Okay, sorry for the unsharing my screen. I was just looking for the one command. That command is not listed in the text interface. So that command is like okay. So this command is like this command you can copy here. This is a check verbosity. Okay, this command I think is not here. Okay, so you can enter, and then you can see it's a from 0 to 3. 0 is a default one that like you are. If you take a click on report quality, this will show you only two qualities. One is provide detail about the perform checks, basic failure messages, and the two is same as the one, but with the detail about failures limited to 100 messages. Okay, so let's try the like a one. Okay, now you can see that with the three numbers selected, it gives you the minimum orthogonal quality, which we are also getting by default, and it is giving us maximum cell skewness is next. This is same as the roughly it's the same as the skewness. This is more has a more like information for the volume cells. Skewness is for the two-dimensional cells. So cell skewness index is like skewness based on the volume cells. Okay. And then we have the maximum cell equivolume skewness. This is like a 0.4. And then we have the maximum exit ratio, the 4 point something. And the minimum expansion ratio is equal to something like that. Okay. So you get more information, but with this information is useful to you, then you can check it, use it. But I don't think that we need the information more than the like orthogonal quality and the aspect ratio. That's more than enough for the majority of the CFD cases. That's enough for our purpose. Okay. So when you display the mesh, you can display the mesh like either faces or you can display the edges. Edges means that you can display the mesh lines also on the geometry. So from here you can display. Okay. So by default, the blue color is for inlet and the red color is for the outlet and the gray color is for the no-slip wall boundary condition. And you can change the colors also if you go there and by type. So if you like go to the outlet, so by default it's a red. You can change it to the light green like this. Okay. And if you reset this color, then you can again take it back to the default color, which is red here. And second option is that like based on the surfaces. So if there are the like 10 outlets and they all will be have the red color, but now with surfaces, every surface has its own ID. So based on that ID, you can actually have the different colors. So if now imagine there are the like 20 surfaces there. So all these surfaces will have the different colors. And these are random colors basically. So this is the one way that you can display the colors by type and by the surface. Any questions?
Professor? Yes, Professor.
Yes, please.
If you change the orientation of the geometry, if, for example, put the horizontal, vertical there, does that affect the results?
Orientation about the geometry in a way that
Yes.
means that the pipe is horizontal, right? Like this may be vertical. You're talking about that thing?
Yes. Will that affect the results? Like the flow?
Actually, at the moment, this pipe has no orientation definition. It's right now, its inlet is along the outlet is along the Z axis. So also we are going to provide the flow along this dimension. And at the moment, we are not putting any gravity effects there. So there will be no body force actually here. So putting them in any orientation will not make any difference actually to the flow solution we are going to get.
Okay,
In
Prof.
theoretical
Hello.
formulation, we drive for the...
Hello, Prof.
Yes, please.
Hello. I think I'm also very
Yes, please.
interested in this question. If this
About the...
geometry is horizontal now, so is it our definition of the gravity that makes it whether horizontal or vertical? The direction of the flow?
Yeah, this will make the difference here. Gravity will make the difference. You can put the gravity here. For example, if you put the gravity in the y direction, that is like negative y direction, this will make the flow heavy. But for this case, I don't think that the gravity will be like that much influential. Okay. So
But
for
if it
multi-phase
is
flows,
vertical, if it is a
gravity
vertical,
is the influential.
hello,
Yes.
Prof.
Okay.
If it is a
I get your
vertical
point. But
geometry,
let's say you are solving the problem like a vertical or inclined pipe. In that case, we have to
Mhm.
include the gravitational effects. Like we have the pipe that is a vertical pipe, and or the pipe that is inclined pipe, like for example. So in that case, we have to include the effects like a gravity effects. Then in that case, this is necessary. For
okay,
this
which
case, this is
direction are
like
we
a
going
flow is
to
only
put
going
this
in the...
gravity first?
Okay, for example, I am putting the my geometry is let's say This is my axis, okay? Y-axis is this and this is Z-axis, okay? So let's say my
Mhm.
geometry was made in this way. So let's draw it, okay? So let's say geometry was not made in this way, but geometry was made in this way, okay?
Yes. Yes.
And if I define the coordinate system, then this is like my local x-axis, y-axis, they are right now Z and the Y. Okay. So
Yes.
they are the local x and y-axis. Okay. The third dimension is like x-axis that is like going to normal to the wall, and that's not useful for the any definition. So the flow is right now is going in this direction. Okay. That is inclined to the like our definition of the x and y, local x and y axis. So in this case, the flow will be going in this way,
Mm-hmm.
but definitely this will get affected by the gravity. So in that case, the gravity will be like in a minus y direction. So you have to put the value here, minus 9.81.
Okay.
That's all.
Okay, Prof. Another question, just a quick one. If
Yes,
this
please.
geometry is 90-degree, that is vertical, without a slant, without bending, is it still also negative y?
It's still the same thing. It's still if the
Okay.
definition of your axis is like z is here and this is like, then if you want to add the gravity, then this is going to be the gravity will be the minus y.
Okay. Okay.
I would suggest one thing, that go for the like one problem from the fluid dynamics book. I have mentioned the one book that is Frankham and White. Or I think you also go with the one more book that is by the Sangel. Okay, so let's search for the inclined pipe.
Okay.
This pipe, they are trying to find out the values of the, I think, pressure difference here. So in the certain industrial process, aisle of density rho flows through the inclined pipe in figure C31. A U-tube manometer with the fluid density PM, rho m, measures the pressure difference between points 1 and 2 as shown in the pipe flow is steady, and the pipe flow is steady so that the fluids in the manometer are stationary. Find the energy expression for the P1 minus P2 in terms of the system parameters. Discuss condition of the H necessary for there to be no flow in the pipe. And what about the flow up from the point 1 to the 2? Okay. What about the flow down from 2 to 1? So I think in this case, you can set a problem by your CFD. Like you can include the manometer also. But now I don't know that in this case, like if the manometer is having the mercury and you are putting the oil here. So how you are going to model this geometry? This geometry will be not very much difficult actually. And you can have the like mercury here. So now you have to solve the problem. So you have to include the gravity and everything there. So what will be the pressure difference between these 2 points? And even without the, like, for example, without the manometer, you can take the 2 points, 1 point here, 1 point here, and you can find out the pressure difference between these 2 points. And then solve this problem analytically. Okay. And try to see that the what solution you get from CFD and what solution you get from the theoretical formulation. And same case may be true for there are many problems you can find out. Like here, you can see this is the problem. So vertical here, if the gravity is important, then I would be putting the like gravity in the minus y direction. Okay, if this is a y direction, then I will put the minus y direction for gravity. This is also another example that will be like gravity effect may be important here. In this case, rho gh. Okay.
Yes.
Rho gh.
Thank
Rho
you.
gh is basically the pressure that is being produced by the gravitational effect and the height. So I would suggest that if you really want to learn something, then I would suggest that make this geometry not very difficult case or very complicated case, but very simple case, and try to solve that case with the help of the CFD. But try to make the problem as a one single fluid. Okay, if you go into the like a two fluids, multi-phase fluid, and then the problem complexity will be very, very high. So at this point, I would suggest that go with a problem that you can make it single phase, single fluid, or maybe you can simplify that to the single phase.
Okay, Prof. Thank you.
Okay. So you should be able to solve this problem very easily, I think.
Professor, a quick one.
Yes.
Now, based on your experience, for example, if a pipe is slant, is the maximum velocity again at the center or changes?
Maximum?
Yes, maximum velocity.
What maximum value? Maximum value of the?
Of velocity or the fluid flow.
Yes, maximum velocity will always be in the center. That is from the theoretical analysis we did first, second or first class. The maximum velocity will be in the center. Okay. That we will also see very shortly.
Oh, thank you very much.
Okay. Okay. So we can turn off the gravity. It's a steady state, pressure based. Pressure based and density based is like when you go for these two methods. So in the one case, when the density is not a function of the like a temperature, means when density is not varying a lot, then we can solve this problem like a pressure based. Okay. So whenever you go for density based, the density based means density is a function of the temperature. It's not always function of pressure, but it's always function of the temperature.
Professor.
Mm-hmm.
Yes, thank you very much on that slide.
Yes, please go ahead.
Yes, I'm much interested mostly, for example, in the nuclear power plant, we tend to look at the transient scenarios. Yes, I've seen there's a
you are talking about transient problem, like transient. What type of the physics will be there that require the transient?
Yeah, for example, there's lots of coolant in the pipes. The nuclear reactor tend to look at transient. So I've seen that there's time, there's steady and transient. Is it the same way? Just below the red line you have drawn there.
Like you are saying that the transient simulation and steady state will be same or not? You're saying like that?
Yes, I wanted to understand the transit. How is the transit applied in terms of this calculation?
Different than the steady state transient case?
Yes, yes. Because I've seen there, in this slide, there's somewhere there's steady and there's I think transient there. So below, after, just above gravity there. So I wanted to know in what state do you put transit calculation in this calculation?
Can you send me in the chat so that I can understand this question fully? Can you type it in the chat while I'm explaining something here?
Hello, Prof.
Can you do it, please? Yes.
Hello, Prof.
Yes, please. Yes. Yes.
I think one thing that is a general problem in CFD is to match the Navier-Stokes equation that we are trying to solve in most problems with the ANSYS interface. Can we relate these two together?
In the ANSYS? Okay.
Yes, you know, we generally have a working equation, which is a Navier-Stokes equation.
Yes.
And what we are trying to do using ANSYS as a tool is to solve the equation. If I'm correct.
Okay.
Is there a way we
Yes,
can
right,
match is there a way we can match these two together and say, okay, here, this is what we are doing with the tools. Here, this is what we are doing with the tools. Maybe try to dissect the equation and relate it with the tool so that we can have a proper holistic understanding of the relationship between the equation and what we are doing using the tools to solve. I don't know if you get my
So you want to
question.
learn about the what is going behind the software.
No, not what is going behind the software. You know, we have an equation. Are you getting it, Prof? We have a Navier-Stokes equation.
No, I'm not getting. Can you? Yes, we have the Navier-Stokes equation, right? Correct.
And what we are trying to do with ANSYS tools is to solve the Navier-Stokes equation, right? If I'm correct.
Yes, correct. Yes, correct.
Is there a way we can merge these two to have a proper understanding and see how we are using the tool to solve the problem, to solve the equation?
Actually, have you gone through some courses on the fluid dynamics, not fluid dynamics, but CFD courses in your undergrad or in your master's degree or whatever degree you are studying? Have you gone through the CFD courses?
What I've done is on my own, is to read some books and try to derive some of the equations, which you also derive at the beginning of this course.
Yes, actually, when you go with like a CFD courses, what they teach you is that they start with the very basics, like how to convert any simple problem to the differential calculus, and then from differential calculus to the algebraic equations, and then apply the different techniques to solve those equations there. Okay.
Mm-hmm.
So they have a lot of theory is there that can they teach you in those courses that how to convert those equations and how to solve those variables like different parameters. Like for example, solving this derivative is easier because time will always march in the forward direction. It's easy to solve because we know that the solution at the previous time step is known to us, and we are then from this we are finding the solution on the next time step. It's very easy to find out. But non-linear terms like multiplying the velocity with the derivative, they are always difficult to convert them into the some expression. So we have to linearize the terms. So there are a lot of theory that is happening there. And now we have the equations that are defining the whole process. So now just imagine that what we are doing. For example, here, if I go to my slides here, for example, I can show you one thing. I've not gone through those slides yet here, so I will actually have to go through those slides. So, for example, we have gone through these all equations. Okay. Now, see this equation that we have said this thing that this pipe flow. Now this is when you are defining the flow. We defined the flow by ourselves. We didn't take any gravity effects here. We didn't take any other effects. Maybe we can take the effects. Maybe we can say, okay, there is some leakage because and that is like introducing the velocity component v is equal to some value. So if you put that value into the function, and then the equation will be different. And in a similar way, you can also introduce that the gravity is there. So that is a body force. And body force is coming here. That is the rho gx. Okay. So right now, this is the gravity in the x direction. If you're talking about x component, then you're talking about gravity in the x direction. If you're talking about the y component, you're talking about the gravity in the y direction. So the gravity forces are there. So if you introduce them, and now if you take a look here, now this is gravity effects may be very much they may be there, but their effect is not significant in the problem we are solving. So other terms may have the like a lot of large values, and if you compare the values here, the gravity effects may be very, very small. Okay. So we didn't introduce the gravity effect in this equation. So from here, when we drive the equation, we come up the formula that this pressure gradient is related to this shear stress. Okay. And the shear stress is like containing the derivative of velocity with respect to the y. So we have the change in the velocity with respect to the r, but no change in the velocity with respect to the x direction because the flow is fully developed. So now in this case, like we are only having the mu. That is the this is the laminar viscosity. This is the velocity of the fluid. That is the laminar viscosity. And because it's a laminar viscosity, so this shear stress is known as the laminar shear stress. So if we have another term that is like a mu t, and similarly we have the same maybe derivative of velocity with respect to the y. Similar term like we have here. This is like having turbulence now. Now to find out this turbulence, we have to have the like two equations like k and epsilon. So they have come up with the equation that if you can find out the k epsilon, and we can have some ratios of k epsilon, that will be equal to the mu t. So now we have the like this laminar viscosity, this is the turbulent viscosity. So whenever pipe flow has a turbulent effects, in that case, the wanted to know about when to apply the two. Two means which two, which is the one and which is the second number. Okay, this pressure based and the density based and the steady state and transient. These two you're talking about?
Yes, Professor.
Okay, so okay. So pressure based and the second one is the density and the okay. Okay, I will discuss this thing. So now see, now here if you have the turbulence quantities here, then you go for the turbulence model. So the whole problem is like revolving around the finding out the turbulence parameter, that is turbulence viscosity. So this is not a fluid property, this is a flow property. So question is that how to find out this value. So there are the various methods like Prandtl come up with the mixing theory, and then we have the very simple like a turbulence model, but they require the like a tuning for the every flow. Every time you have to put some parameters to solve that particular problem. So they wanted some universal turbulence model. So then they come up with like k epsilon, k omega type of these equations. Okay, so if we talk about the like these two problems like pressure based and density based. So in the very simple words, okay, we go for the pressure based when the flow is incompressible. And what is the meaning of incompressible? When the Mach number is less than 0.3 everywhere. It should not exceed 0.3 in any location due to even the acceleration of the flow. So pressure based is applied in this case, okay? But pressure based has now like four algorithms. One is the simple. These are the velocity pressure coupling. Simple, okay? And the simplex and the piezo. Piezo and simple, they are exactly same. If you remove the transient term, the piezo will be same as a simple. So piezo is for the when we are solving the transient cases. So we take this pressure velocity coupling for the transient cases. But then they have the like for some time now they have the another solver that is coupled. Okay. So now we can have the like when you talk about Navier equation, there are three equations actually. Generally speaking, there are the two equations, continuity and momentum equation, but generally speaking, there are three equations. One is the continuity equation, conservation of mass. Then we have the x momentum, we have the y momentum. Momentum equation, three components, and z momentum. Okay, and then we have the energy equation, and then comes the turbulence. Then comes the species. There are maybe two species. Now to solve the species and find out the number of the species in the domain or their ratio is another equation, okay? So continuity equation and the momentum equation. So they will decide about the Now, continuity equation was only about the flow rate, okay? But when they are combined, they both share the a pressure field and the velocity field. They both share the velocity and the pressure field. Because the flow rate will be affected or will be directly function of the pressure gradient. So continuity equation is not complete without the pressure gradient. And the x momentum, y momentum, z momentum, they contain the velocity derivatives, and also same as a continuity equation, also they have the pressure difference terms. So when we want to solve them, the pressure field and the velocity field should satisfy both of them at the same time. So when we solve with the simple simplex and piezo, what they do is that they convert them into the equivalent form that contains the pressure terms in the continuity equation. So they solve the momentum equation, they get some pressure field. They put the pressure field into continuity equation, and if it is satisfied, then it's okay. Otherwise, they will go for the loop. This is based on these methods, simple, simplex, and piezo. So this is suitable for the cases when the Mach number is less than 0.3. But now then they have the density-based solver that is suitable when Mach number is greater than 0.6. So now problem is that what should be between the 0.3 and 0.6. So neither of them, simple, simplex or piezo, and are the density-based solver, they are suitable for the range between these two flows. So what they did is that they come up with a coupled solver. So what they are doing is that in the coupled solver, what they do is that they solve the continuity equation and momentum equation single matrix. So there's no need to be going to and fro from the continuity to momentum to continuity. So they solve in a single matrix, but they require more memory as compared to simple simplex or piezo. But they can come up with a solution in a very few iterations. It will take more time for one iteration, but this will require less iterations. Okay, this is like a coupling the momentum continuity equation in a single matrix. And density-based solver is same as a coupled one, but they will be solving in a single matrix. What they are solving the continuity equation. They are solving the momentum equation, and they are solving energy equation. Why they are solving in a single go? Because the density which we are getting as a function of temperature will be from energy equation, and those densities will be affecting the continuity and momentum equation. Definitely, the m dot is equal to the function of the rho AV, and also this will also affect the pressure there, because the equation state is the pressure is equal to rho RT. So this will also affecting your equation state, that will be contributing to the parameters over here. So that's why they are solving all the equations in a single go. But that's the most expensive thing. And that's why I told you that for 1 million cells, we may require 2 GB RAM. That is when we are solving simple. Coupled may require 2.5 GB or 3 GB, but for the density-based solver, we need the 4 GB RAM. So when you go with the density base, this is for the missile simulation, aircraft simulation. So any flow with a more than higher than the Mach number, which is 0.6. So greater than Mach 0.6, we should go for the density based solver. And below 0.3, go for the simple, simplex, piezo. And coupled solver over inside the pressure based is it can solve the flows of Mach number less than 0.3, or even it can solve the flow Mach number a 0.7, 0.8. Doesn't matter actually. Okay. So I think you understand this thing. Then the second thing is that you're talking about when we use the steady state or the transient. So see, some problems, they are the solution may evolve. Like for example, I'm talking about, for example, a room. Okay. So, or maybe the pipe. So pipe has when you start to open the wall on the inlet here. Okay. What will happen? Pipe will be being will be filled here, and then it will start to flow. And then it will completely fill, and then the flow will be a very continuous. So maybe you're interested that how much time it will take to reach the 100% filling of the pipe in some application, like the the pipe transporting the oil to some other location. In that case, maybe you're interested for that thing. In that case, the transient case may be important. But right now, I'm just finding out that when the pipe is flowing and flow is flowing in the pipe and it is going to start to give this much flow rate to the other side. So I'm just finding out that, okay, it is providing that much flow rate or not. In that case, I will not go with the transient case. I'm not interested that how the flow is evolving to this final state. So I will not go for the transient case here. Okay. But I'm interested for the case that how the the flow is evolving to its final state and I want to see the intermediate states. Then I will go for transient case. And another example, for example, I can give you idea here. For example, there's a room. And the one side is being affected by the sunlight. Okay. So maybe this is made from the glass, this side. And also we have the air conditioner installed over here. That is providing the cooling to the room. So now I think if you go to understand to the very basic of your undergrad, you will know about the thermodynamics. And the heat transfer. It's very confusing to know that where we apply the heat transfer and when we apply thermodynamics. So it's very simple to understand. Thermodynamics we apply when we have the energy balances. Okay, so we're not interested that how that transfer is taking place. So, but the heat transfer is about this is like a subset of the thermodynamics. But we're interested that how the heat transfer rate. We're not talking about heat. We're talking about heat transfer rates. So how they are evolving. For example, there's one air conditioner and we have the sunlight that is may raise the temperature to very high degrees. So I want to see that in some applications that if the room is hot and I've turned on the AC, maybe I'm a company that is manufacturing the air conditioner and I want to be very much competitive in the industry. So let's say, are in the market. So let's say the one air conditioner is can cool down this room in 30 minutes. Okay, now I'm installing my air conditioner. Then I want to see that in which time, how much time this is going to cool down the same room, the same condition in the less time. So then I put my air conditioner turn on. Then I found out this will take the 20 minutes. Okay, so in this case, a transient case is important. Okay, but if I'm solving this case and I'm finding out, okay, in the equilibrium condition with sunlight applied here, air condition applied here, what will be the temperature of the room after whatever time it is? So what is the temperature of that room after these energies on the sides of the room? In that case, the steady state is enough. But if I want to find out that how much temperature will be on this wall because of the sunlight, how much cooling will be there because of this air conditioner here, then and how much time it would take, this is a transient case then. So now question is that as engineer, are you interested for the transient cases or not? Are you looking for the only the a steady state case? So for example, the geyser. Okay. And pardon for my spelling. So for example, the water geyser, that is to provide you the hot water in the winter. So have you ever studied the how much time it will take to heat up the water? No, I think I never did this thing. I just turn it on and after half an hour I will go to the open the tap and I will see that if the water is hot or not. If not hot, then I will wait for the maybe 15 minutes more. But I never studied this thing that how much time it will take to reach some temperature. And even I don't know the temperatures when the hot water is coming from tap from the geyser. Maybe it's a 70 degrees Celsius. I don't know. Maybe it's 80 degrees Celsius. I never know because I have the one hot water tap, one cold water tap. I will open them together and I want to have the temperature that is comfortable to my body. Okay. So I never gone for this study. I'm not interested for the transient history here for my geyser working in my house. Okay. I think I'm clear about this thing. Okay, so now we are going to use a pressure based, velocity is very low and it's a steady state. So the first thing is that you have to like turn on the laminar flow, because the Reynolds number is less than 100. So flow is going to be laminar. Then we are not going to use the energy equation because we are not interested for the temperature field. Okay. No radiation, no heat exchanger, no species, no discrete phase, nothing else. So now materials. Here I'm going to, either we can define our new material. For example, I can say click on create edit and put the new name as like my fluid. Okay. And I can put the my properties, which are the gravity is equal to, density is equal to 1 and viscosity is 0.01. I can have my own fluid. Okay. So it will overwrite over here. Otherwise, you can also define the new material, like for example, the air, and copy. Okay, and be careful with the one thing. Let's say if I delete my material. Okay, so right now it's being used by my domain. That domain is a sales zone condition. If I go to there and this is my domain name, solid name doesn't matter. Actually, type of the domain is important. So name can be anything, but the type of it should be fluid one. Second is solid. Solid means it's only used for the heat conduction, not for any flow. So here you can see that we have the like two fluids. So right now my fluid is there, and if I change to the air, now air will be working fluid for my pipe. Okay, just example. Okay, now if I go back to materials and I want to delete my fluid here, then I can click on delete. Okay. Okay, now go back to air. And let's say I define the air density, now density as a 0.1 and viscosity as a 0.01. Either you can override the air properties for this case only, not for the database. For this case, you can override, or you can define your own material like a my fluid, but you should not be overwriting. So my material, my fluid, and then click on change create. And when it asks you that change, create mixture and override air, no, say no. This will like keep the air as it is, and it will create new fluid with the name as a my fluid. See here, okay? You can close, but the thing is that if you go to sales zone condition, it should be using your fluid, as my fluid, okay? Click on edit and choose the material name to my fluid. And this is true for if you're molding in the heat transfer case, maybe you're molding some solid bodies around the fluid bodies. In that case, you have to define the proper material for that solid body. Okay, for that, you have to like go to sales zone conditions, select the sales zone condition here, click on the edit, and then select the proper material and the other properties maybe. Then we go to boundary conditions, and you can like arrange the boundary condition by the zone types, like inlet, outlet, wall, interior, like that. So on the inlet, we have the flow velocity we drive is equal to 1 meter per second. It's a 1 meter per second. And outlet will be like a zero gauge pressure. So it will be always zero gauge pressure, but just make sure that the pressure outlet is defined in the type for the outlet boundary condition. And the wall will be no slip condition. Just confirm no slip condition is there. It's a stationary wall and no slip. Okay. Close, and interior should be like, it should be the fluid. Okay. Okay, next thing is the method. So we have the two solvers. I told you the couple will be solving the continuous equation, moment equation in a single matrix and simple. Sometimes the simple may work, but the coupled may not work. In some cases, coupled may work and simple may not work. Okay, in some cases both can work. So you have to check that the which is like more efficient for your problem. So like right now, choose a simple here. Okay, and keep the default settings here, like gradient, least square, cell based, pressure second order, and momentum as a second order upward scheme. And please keep this thing in mind that the momentum equation will always be like a final solution, should be solved with the help of the second order upward scheme. But in case you have the difficulties in solution convergence, then you can start in the beginning, you can use the first order scheme, like first few 10, 20, 30 iterations, then you can switch back to the second order upward scheme. For example, right now I'm choosing the first order upward scheme. After 10 iteration, I will switch back to the second order scheme here. In the controls, we can actually control the equations parameters. So how solution will progress depends on the under factors. So if you put the higher value, you can get solution few iterations. If you put the low value, then the solution may go for the more iterations. Okay, so I will keep the default setting right now. Report definition, maybe we can put the some point here. So let's say if I display my mesh without the mesh lines. And colors I'm going to choose by the type, default one. Okay. And here you can make the transparency here, but transparency will be applicable on all the walls. Okay. So if you go to view menu, from the view menu, actually you can control the transparency of each and every surface separately. Okay, one by one. So click on compose and you can see where the wall condition here. Click on display. So actually you can show the mesh lines. You can show the outer faces. Outer faces are the faces which are facing to you. If you don't select them, they will be hidden from the view. Means that you can only see the like a back side of your geometry, but not the front side of the geometry. For example, here. So you can see the front side is not visible. You can see the back side. And that's why you are able to see the geometry from inside. The outlet you can see right now. Okay, but if you turn on the outer faces, then you will not be able to see the outlet from here. Second thing is transparency. Transparency means that like we have the transparency of right now 55%. So 45% will be opaque and 55% of the geometry will be like this surface will be transparent. So it's a different than the like outer faces. Now all faces they are displayed here, they will become transparent. All faces will become transparent. Again, you can see from inside. Okay. You can also change to some other values, some high values. And in the same way, you can change the color of the surface. Like you can change the combination of the colors, numbers, red, green, and blue, and you can find out, you can get the different colors on the surface. Okay. So now just close the everything. And one more thing is that I want to overlays. So overlays means that this will be displayed forever. Even if you go for some new graphics here, maybe some plots here, this will overlapping the existing graphs in the same window. It's the meaning of overlays. That this will not replace the old graph will not be replaced by the new graphs. Okay, all will be in a single window. Okay, I want to create a 1 point, so I will go to results and click on the. Also, this can be done from the domain. So create and the point. Same thing can be done from the results and surface and create. Same thing here. So create and the point. I want to create the point at the center location, but in the pipe that is in the fully developed region, that is the flow is fully developed. So I don't want to put the point where the flow is developing here, our entrance region, but I want to rather put the point where the flow is fully developed. So that is like maybe after 10 meters. So I'm to be on safe side. I want to be that point on the 25 meters or 20 meters or maybe 30 meters. So that is 25 meters. And I want to put the point on the center line. So Z, X and Y both are 0. Okay, so put the name here, point Z is equal to 25 meters. So I can identify the point by its name. So the point is a point and at the location Z is equal to 25 meters. So click on create. Okay, so you can also manage from here and you can delete the old point from here, the old surfaces from here. Okay, now again do it same thing here. So create point and X and Y 0 and Z is equal to 25. It's a point at the Z is equal to 25 meters. So click on create. Okay, now if you display your geometry, so this time because we have the overlays already working, so there's no point of actually displaying these surfaces. This will like be writing them again here. Okay, so like unselect them all and then just display the point. This is like now on the list here. So you can see the point is being displayed here in the center. It's just in the center. center of the pipe. Okay. So on this point, actually, I want to see the velocity change when solution is progressing. So I want to see with every iteration how the solution is progressing on this point. And based on that point results, I can actually can access or can decide about the convergence of my solution. So the result plots, they are important, but also you should be monitoring based on the your requirements as well. So now we have the report definition is placed here. So you can right click here and you can delete. So you can put your new surface monitor. It is going to be vertex average, point number 05. And this is like you can put the name as the surface monitor, Z25 meter and velocity. Okay. So field variable should be velocity and it should be like, it should make the report file. And that file will be written on your hard disk. You can like open any time, even after solution has been done and file is closed. And you can also open that file into the Excel. The report plot will be plotting that data on the screen. And print to console means this will be writing down data on your computer over here on this this message window inside the Fluent. So this will be writing the files over here. Okay. So you find out in the monitors, you will be seeing the report file and the report plots. Okay. And you can delete the old files which are here. Right click here and delete. Okay, in the residuals, you should be putting the more values here so that we can converge them to like if you put the like a tight convergence here, then the solution will not give you message. Solution has been converged and solution will not stop. So what I want that the solution I should stop after the my criteria like the surface monitor at the point is equal to Z is equal to 25 meters. It's a now straight line. And same is the case with my continuity and momentum equation residuals. So once I can visually inspect them and I can see them and satisfied with my results, and I will stop the solution myself. That's why I'm putting the criteria which is very, very low. Okay. And initialize with the hybrid method, that is like a very ideal method. And then click on run calculation.
Prof,
So
I have a question.
Yes.
Under velocity inlet.
Velocity inlet.
Under velocity inlet, yes. Sometimes under momentum in velocity inlet, sometimes they change the specification method to intensity and hydraulic diameter. What is the significance of this? They define the turbulent intensity and the hydrodynamic diameter. What is the effect of this in the flow pipe?
See, if you're talking about turbulent flow, in that case, those inlet parameters may affect the solution like boundary layer. Laminar flow, we don't have actually those conditions. We don't have the turbulence quantities for laminar flow.
Okay.
But for the turbulent flow, we have the like a turbulent intensity. Turbulent intensity is nothing but a variation of the velocity. For example, we have the velocity that is, let's say, right now in our pipe case, the velocity inlet is 1 meter per second.
Mm-hmm.
Okay. So what does it mean? It means that if you take a look on this graph, this is like velocity and the time. Okay. So this is like a constant value right now. Clear?
Mm-hmm.
Now this is value is the 1 meter per second. Now just imagine that we have the velocity and that is varying somehow like this one. Not equally, but maybe randomly. Okay. And on the one side, the change is like maybe its change is the 0.1 meter per second. So change from the mean value, which is 1 meter per second, this change may be equal to 0.1 meter second. So if I divide this deviation from the average velocity, this is my fluctuations. This is the fluctuating component of the velocity. How much fluctuation we have in the velocity from the mean value. This is like a change in the velocity at every location. So maximum change we have the like a 0.1 meter per second. Okay. So if I divide this change in the velocity with the average velocity, then I will get the value as a 0.01. Sorry, 0.1 divided 1 is equal to 0.1. So if you multiply to get the percentage, if you multiply by 100, this is going to be the 10%. So in this case, the turbulence intensity is equal to 10%. Because turbulence is the disturbance in the flow. So now to measure the disturbance in the flow, we use the turbulence intensity, that how much turbulence is there. So high turbulence means that we will be deviating much from our average flow velocity. Okay, and less deviation means that we are like more towards the laminar flow. This is the definition of the like a turbulence intensity. Okay. So it depends on the different flow parameters. For example, in the case of wind tunnel, the turbulence intensity may be very low because they keep it to be very quick. So it's maybe like 1% or maybe 0.1%. In free stream flow, turbulence intensity may be 5%. In the case when the flow is coming from the combustion chamber, in the gas turbine engine flow coming from combustion chamber and going to high pressure turbine, turbulence intensity may be 20%. Okay. So it has to be like the value that is the particular for the particular situation. That value should be inputted to our simulation. And one more thing, that there are the many questions that you want to answer. I would suggest that follow some standard procedure. So question is that how you will be finding out the standard procedure. So go to some papers, some thesis, like for in your field, like some MS thesis, maybe some PhD theses. Okay, go to them of high quality from good universities, and try to find out that how people are solving their cases. Like for example, if I give you one example, that let's say I'm plotting that control plots, pressure control plots on the wall of the cylinder. Okay. So when I was at your stage, I was wondering that what does it mean by these bands. Okay. So I was trying to find out the values, that why we have the band of this much, not up to here, why it is over here. In some pipes simulation I've seen up to here. So I worry a lot. I worry a lot. So for these things. Now, if you just imagine the complicated geometry, like maybe a turbine blade, and that blade, the pressure controls may vary a lot. So you cannot comprehend that thing from those graphs. You have to run the case, and you have to find out the quantities. Okay. The quantities are to be compared and to be comprehended. These plots cannot be comprehended. We can generally see what does it mean. Maybe we have the pressure high and low pressure, and in between we have the high pressure, and two sides we have the low pressure. This is not possible physically. Then we have to look for the solution. So generally speaking, these plots will give you the idea about the flow, how the flow is behaving. If this is the correct solution, then it will give you idea about that particular device or system. Solution not correct, then it will give you idea that the how solution is wrong and where solution can be wrong. Okay, and why it can be. So I think that we should be these questions are important, but having the sound understanding of the theoretical concepts of the problem, theoretical concepts and the aspects of the CFD, fluid dynamics, heat transfer, mathematics, and then go with the proper application of the softwares. Or if you make your own code, then it should be properly done then go for the solution and try to find out the numbers. Numbers are more relevant for the understanding the problem. Okay, the numbers are correct, then the solution is also correct. So here, okay, so based on the surface monitor, I can see solution has been converged. Now it's a straight line, and same is the case with the residuals. So you can see after 100 iterations, the solution is not changing much. Okay, and in the case of the velocity monitor, I can see after 40 iterations, the change maybe is here, but it's very small. Okay, I can get the more information about this velocity convergence plot from the text values. You can see after like 40 iterations, like go to 40 iterations based on the graph, 20 iterations maybe, but go for the 40. So after the 40, the value of velocity is on the center point at z is equal to 25 meters, is the velocity is 1.897. So 1.89, 1.9, so 1.9031. So at 66 iterations, like over here. After this point onwards, the value is not varying. 33, 1.9, 1.9033 is achieved at the which iteration? At 82. So after 82, you can see, you can compare it like it's like around 100. So this is same as 82 and the 100 is same. So we can see that the after 82 iteration solution is not now is converged. Okay. Now solution is wrong or right, it's a separate thing. Like we have to compare with the results with some data. Solution may be wrong, may be correct, but solution has been converged. This is a separate thing. This is related to CFD theory. So solution has been converged based on the residual plots and the surface monitor, but velocity value may be wrong or right, depends on the our database from which or with which we are going to we want to compare our results. Okay, any questions?
Sir, I have one question.
And tomorrow we are going to yes, please.
Sir, what is Y plus in CFD?
Y plus is actually a non-dimensional wall distance. Okay.
Wall distance.
So you will ask, and what is the meaning of this thing? Actually, see, like we are solving the problem here. Okay. Flat plate again. So at every location, the boundary will be like will be like thickening, and it will be like going in this way. Okay. This is how boundary will be developing over the wall surface of the flat plate, simple flat plate. So at every location, you will see that this will be like having this velocity profile on the every location. Along the y-axis, it will have the variation. And this point is a point where the velocity u is equal to 0.99 times of the free stream velocity. Free stream velocity is coming from the left side. Okay. And the second profile is over here. Okay.
Okay.
Now, question is that, for example, I want to solve this problem. So I know that the here profile is very steep, and then it is gradually the slope is like becoming more flat and flat. It becomes 0 at this point maybe. Okay. So I need more cells here. So based on I know this, let's say this height is 0.2 meters. So I want to like resolve this profile. So if we resolve this profile, then I need more points here. And maybe bigger, less cells over here. So I will make the mesh in this way so that this can cover the points like this way. Correct, right? Now this is okay, for this profile at this location of the, let's say x is equal to some value. Okay. Now what about the mesh size? If you talk about the boundary layer over here, so maybe the less cells here. What about the boundary layer here? This is like even increasing more. So we have the velocity profile, and it may vary from case to case. For small geometries, their size may be small. For large geometries, like a A380, the size of the boundary may be very, very large. So deciding the mesh to resolve this geometry, the flow here is very much difficult, and it will be like a subjective thing. Okay, it will be subjective thing. So what they did is that they come up with a universal like profile. They say if I, instead of the, let's say this direction, this is the velocity here. Okay, this is the like y direction, and this is the velocity scale. See, this is the y. It's varying in the y direction, and on the fixed x location, x is fixed here on this location.
Yes.
But the velocity is varying. So velocity scale is on this side. Zero velocity, some velocity, and this velocity at this point will be the 0.99 times of the u infinity. Okay, so they are like a dimensional velocity u and dimensional quantity y. Now, if I define the some non-dimensional quantity, let's say it's the u plus the y plus. So what I'm doing is that I'm dividing the u by the u star. The u star is basically is the friction velocity that is equal to the u tau, wall shear stress. Oh, sorry, the friction velocity. This is equal to the wall shear stress divided by the density. Okay, because the locally on the wall we have the wall shear stress, and wall shear stress is nothing but the gradient of the velocity minus mu and partially by partial y at the y is equal to 0. At this point y is 0. So for all points of y is 0, but the second location of the y is varying for all profiles. Okay. So now the wall shear stress is nothing but a velocity gradient, simple thing. So these all things like they will determine the profile shape and its behavior. So they come up with the equation that the u plus is equal to u upon u star is basically is a u tau. Okay. Y plus, they have the equation that is equal to the like delta y, the first cell height, and then they have the like what this u tau density divided by viscosity. So they are talking about, they are taking into consideration the viscosity of the fluid, density of the fluid. They're talking about the first cell height of the your cell here, and they talk about the friction velocity, that is like a velocity at the very close to the like on the wall. So let's say you are talking about the y plus is equal to 1. So you know that the density is of the fluid is known, and so is the case of the viscosity. So we know about the density and viscosity of the that fluid. Now mu t, if you are like solving it for this one, and you know about the value from simulation, but if you are late, let's say you are not still not, you didn't start simulation, you want to get the idea of first cell height. Okay, so that is like you can find out from the empirical formulas, like the wall shear. This friction velocity is equal to the under root of the tau wall divided by the rho. Now I can find out the tau wall by this equation. The CF is equal to the CF, coefficient of friction, is equal to, I know this thing is the tau wall, okay, divided by 1/2 rho v square. This is the u infinity actually. So from here, I know the correlations of the CF in terms of Reynolds number. So from here, I can find out that I can find out the wall shear stress as a CF into 1/2 rho u infinity square. And CF I can find out from the their corresponding relationship based on the Reynolds number. Okay. So now I can estimate the value of the first cell height based on the my y plus requirement. So what will happen? First thing I will tell you. This will all profiles will convert into single profile. This will be single profile. And scale is the u plus, on the axis, and y axis will be the y plus. So instead of the having these all profiles, now we can, and
Are
this
you
is
there,
true
sir?
for the every flow in the whole world. Every flow in the whole world. Okay. So if you take this solution of the in the lab for the some surface and then like convert them into the y plus u plus, you will see that the all profiles will have the same shape, same values. Okay, they will be exactly overlapping, and that's why we call this profile as a universal law of the wall. Universal law of the wall. So on the wall, surface in any flow, this will take in non-dimensional terms, U plus Y plus, they will take the only single profile. Okay. So on this single profile, actually, we can set the our first cell height. This first cell height is based on not Y plus, but based on the Y plus. So we said that okay, the first cell height should be Y plus 8 equal to the around 1. Now, corresponding value of the first cell height in terms of delta Y is like will be different for the different flow conditions, different geometry size, and the different conditions over there. Okay. So this is like a theory about this Y plus and the U plus. Okay.
Yeah.
So we see this thing in the flows when we have the turbulent flows, but this is the idea about this Y plus and the U plus.
So, sir, the point which I got from your talk is that like Y plus, it's all about the external flows. We used to calculate this value for the external flow only, not internal.
Internal flows, also for internal flows, Y plus will be there, boundary will be there. So internal flows also be being affected by the Y plus values also, definitely. But see, internal flows, see one thing. If we talk about the pipe flow, it's internal flow, okay? So internal flow has to be resolved with enough mesh there. So if you resolve this flow properly, then Y plus will also be taken care very, very carefully. But for external flow, because this whole pipe flow is in the boundary layer. For internal flow, all the flow will be in the boundary layer mostly. Okay. But for external flow, there's some region that is in the boundary layer. So that's why people are like more concerned in the external flow. But because that region, we don't know how much region is there. So that region should be resolved properly. So making that region very large, we can have the like more cells in the more height, and that region may not be resolved properly by that much cells in the. So maybe instead of the having the like 1 meter of that boundary layer, maybe we assume this is 5 meter. So instead of putting the 40 cells, 40 layers in the 1 meter, we're putting 40 layers in the 5 meters. So definitely we under resolving the 1 meter region of the boundary layer. That is more concerned like in the external flow as compared to the internal. Internal flow, we directly take care of the, because mesh requirements are already there, that is to be resolved by this much of the, for the geometry resolution, this much should be there. At this point, flow is this flow is this. Internal flow, we have a very small like area portion. So that we automatically take care by the meshing mostly. But for external flows, the domain size is very, very large. And the boundary is like maybe 10% of the chord length. If we talk about the aerofoil or wings, it's not more than 10% of the aerofoil. So that's why it's a more concern in the external flow. Okay. I will be leaving with one question. Then I will stop here. I have the one question that, for example, if this is a flat plate and the flow is laminar, means that Reynolds number is less than 1 into e power 5. So flow is laminar, okay? So question is that in the laminar flow, boundary will be also always be there. Boundary will always be there in turbulent flow or the laminar flow. How you decide about the mesh sizes? How many layers should be there? Based on which criteria? Because in the laminar flow, we don't have the Y plus. Okay? So based on the which criteria, we are going to decide the first cell height, second cell height, third cell height, overall number of cells in there. So for laminar, let's say take example of laminar flow over the fluid plate. So how you decide about these meshing parameters? Because there is no Y plus. Okay, let's discuss this thing tomorrow. Okay, search the Google and
like,
then
we
let me
will
know tomorrow that how you
and it's my guess. Like we will discuss, we can guess that laminar flow with the distance of the plate, as the plate is the distance is increasing, the dimension is increasing, that will tell us about the nature of that flow.
It will become the.
Sir, can you repeat your question?
I'm saying that, for example, in turbulent flow, if you take example of flat plate, you decide about the first cell height based on the Y plus, correct? In turbulent flow,
Okay.
you discuss about the Y plus all the time. So what is the criteria of the meshing in the laminar flow? Same flat plate, but now flow is laminar. So how you decide the first cell height, second cell, third cell, how many cells should be there, and where more cells should be there? So how you decide about the laminar flow, number of cells, first cell height, second cell, third cell? So any idea about the laminar flow?
So laminar flow, like which has the Reynolds number less than
Less than
one 1 million.
not 1 million, but it's like 0.1 million, less than 1.1 million. This one.
0.1 million. Yeah, 0.1 million.
So then how you decide about the meshing for the laminar flow? For turbulent flow, we have the Y plus, but for laminar flow, what it should be the criteria for the meshing?
Yeah,
This is
so
about
that
based
I
on the
don't
neta.
know.
Neta.
Okay.
Neta. Go for the similarity solution. Search the similarity solution for flat plate. Also search the Blossius solution. Blossius solution for the flat plate. You will not directly find out the how to mesh the flat plate boundary layer, but you will get the idea when we discuss maybe tomorrow. We will get the idea.
Prof.
Okay.
Hello, Prof.
Okay.
Hello.
Yes, please.
Is there any
Yes, I'm
assignment
hearing
to
you.
test? Is there any assignment to test our knowledge based on the simulation you just did?
Not at the moment, but definitely there will be one assignment at least for this whole course.
Okay.
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 Okay. Thank you. See you tomorrow.
Thank you very much. Thank you. See you.
Okay. Thank you.
Thank you. Thank you.
Bye bye.
Bye.
Bye.